Hello, can you hear me?
Yes, we can hear you, bro. Just
So,
let me introduce and we can start.
yeah.
Give me a moment. Okay, so good evening, everyone. Thanks for joining us today in the first talk of the series named Alumni Echoes. With the start of this series, we embark on a new journey of connecting our younger audience of physics enthusiasts with the Department of Physical Sciences alumni here at IISER Berhampur to bring in a plethora of insights from these individuals who hold a strong acumen for pursuing a career in research in their field of interest. We hope this series of talks will be an enriching experience for our audience by giving them a sneak peek into the nitty-gritty of the challenges and opportunities in a given field. There is hardly any doubt that materials have served as building blocks of the things we see around us since time immemorial. Research on these gifts of nature has a long-standing impact, starting from tiny solar cells on spacecraft to electronic devices like mobile phones that are an integral part of our daily lives. Materials have revolutionized everything. However, there has always been a quest to find newer materials that serve as cost-effective and sustainable solutions to our daily problems. One such material is peroxide, which our speaker for today is working on. So, without further ado, I would like to introduce our speaker for today, Mr. Debapratim Pal, who recently graduated from the Department of Physical Sciences here at IISER Berhampur, this convocation that we had. His research interest lies in the interesting material called halide double peroxide. With that, I would request Mr. Pal to begin with his presentation titled Halide Double Peroxide, a new approach for lead-free optoelectronics. Pal, please.
Hi, good evening, everyone. I hope I'm audible.
Yes,
So,
you are.
yes, okay. So, I'm starting my presentation. The slides are visible, right?
Yeah, sure. That's it.
Yeah. So, good afternoon, everyone. I am Debapratim Pal from BSMS 2019 batch. So today I am going to discuss about halide double perovskite, a new approach for lead-free optoelectronics. So these are the contents of my talk. So basically, at first I would like to discuss about what are the perovskite materials, then a brief overview of this halide perovskite material, then some problems which we are facing now, and the halide double perovskites, the synthesis procedures, optical properties, the tuning of optical properties, stability, applications, and the prospects. Okay, so basically the perovskite term, it has come from the name of Russian mineralogist Anton Perovsky. So perovskite is actually a mineral which has a chemical formula CaTiO3, or you can also call it calcium titanate. So in general, the materials which has the similar structure with the CaTiO3 are denoted as perovskite. So the general formula of perovskite is AbX3, where A and B are cation and X is the anion. So X could be either halide or it can also be oxide. And we can get different type of crystal structure depending upon the size of cation and anion. So in this slide, you can see, so this is a unit cell of AbX3 perovskite. As I mentioned earlier, that the perovskite can be divided into two main groups. These are oxide perovskites and halide perovskites. So for halide perovskite, this Xi in this Xi, so there it could be either bromine, chlorine, or iodine. Or for the oxides, this Xi will be oxygen. Okay. So now. The stability of this perovskite structure mainly depends upon three parameters, and these are charge neutrality, because the overall charge, it has to be neutral, and second one is the octahedral factor. Basically the octahedral factor is the ionic radius of the B cation with with the ionic radius of anion. So So you can see here, to get a perovskite structure, this value of mu, it should be from 0.442 to 0.895. And the third one is the Goldsmith tolerance factor. So here is the formula of the Goldsmith tolerance factor, where Ra, Rx, and Rp are the atomic radius um, of this A site, B site, and the X site anions. Okay. So basically this tolerance factor, they decides the structure of the crystal. Like if the value of T is from 0.9 to 1, then the structure would be cubic. And if the value of T from 0.8 to 0.9, then the structure would be either orthorhombic or tetragonal. And also if if the value of T is exactly 1, then it would be a perfect cubic structure. And also, if the value of T is higher than 1, then we can say that this A site cation is too big to be fitted for this perovskite structure. And if the value of T is lesser than 0.8, then this A site cation would be too small for the perovskite structure. So basically, this Goldsmith tolerance factor and the octahedral factor, these works as the sorting hat. Okay. Now, one may ask why we are so much interested in the halide perovskite material, or more precisely, the late halide perovskite material. So, you see, the halide perovskite materials can be divided into two parts. So, first one is the hybrid inorganic perovskite, and second one is the inorganic perovskite. So, in the hybrid inorganic perovskite, the A site, so here will be organic cation, and for the inorganic perovskite, the A site would be either CS plus or RB plus. And here now you will see how important is this halide perovskite materials because of its optoelectronic application. So these halide perovskite materials are used in memory devices, making piezoelectric devices, solar cells, thermal sensors, display, X-ray, LEDs, and for laser production. And yes, there are some problems with this lead halide perovskite. Then the first one is obviously the toxicity of lead, because we all know how toxic is lead, because it causes water pollution. And also the lead has the ability to destroy the work of enzymes. They also causes bone calcification, and they can also lead to nervous system damage. And yes, the late halide perovskite materials are very prone to degrade in the presence of moisture, sunlight, and UV radiation. So in this cartoon, you can see the perovskite decay. It is faster than the speed of flash. Okay. And yes, here you can also see that this late halide perovskites, they show a decrease in the fluorescence intensity and photoluminescence quantum melt. Okay, so to do proper use of perovskite material, we need to face some hindrances. So these are production in the large scale, and we have to overcome this toxicity of lead and the instability of materials in the ambient conditions. So now we have to design a material which can overcome all these issues, and mainly it shows proper stability, and they are obviously eco-friendly, and mainly they would be lead free. Okay. So now scientists have started designing perovskites into two main approaches. So actually they are trying to replace this lead cation. So here are two main approaches. First one is the replacement of this lead ion with homovalent cations, or with cations which show divalent oxidation state, that is the +2 oxidation state. So here you can see one lead atom can be replaced with similar homovalent cation which has a similar configuration with leads, so such as tin and germanium. And also you can replace the Pb2 plus ion with elements which has divalent oxidation states, such as calcium, palladium, cadmium, barium, nickel, cobalt, zinc, iron, strontium, etc. And on the other hand, the second approach is substitution of lead uh, like you can substitute more than one lead cation with different type of uh, elements. So this is known as the heterovalent substitution of lead. So basically you can substitute two lead atoms with one tetravalent atom such as tin and palladium. Just 1 minute. So yes, so to so the heterovalent substitution of lead that can be done by substituting two lead atom with one tetravalent B4 plus atom such as tin and palladium, and you can also replace three Pb2 plus atom with two trivalent atoms, and you can also uh, replace two divalent lead atom with one monovalent and one trivalent atom. But here are also some issues, because you can see here the plus two states of tin and germanium, they are less stable than their plus four state, and also the cadmium and mercury, they are not eco-friendly, and the band gap of calcium, barium, strontium, they are not suitable for the optoelectronics. So comparing all these issues, the scientists have found that uh, the, the double halide perovskites, which has the general formula A2B B dash X6, they are the most suitable for designing the lead-free perovskites. So yes, the halide double perovskites are our new hope, where these materials are designed in such a way that two toxic lead atoms are replaced with one non-toxic trivalent and one monovalent cation. So its name is halide double perovskite because the unit cell of this halide double perovskite, they are twice than the unit cell of halide perovskite. So in this figure you can see this is the unit cell of regular perovskite and this is for the double halide perovskite. And so we have designed the halide double perovskite. So now we have to overcome these issues. So first one is the stability, and second one is the potential for optoelectronic applications. So here are the synthesis procedures to produce double halide perovskites. So these materials can be synthesized in both bulk and nano form. So the nanocrystals can be synthesized by these methods. These are hot injection method and anti-solvent reprecipitation. And also in the bulk state, we can synthesize this halide double perovskite in as a microcrystal and single crystal. So the methods to produce this microcrystal and single crystals are solvent evaporation, solution control, hydrothermal method, solid state sintering, and growth from the melt. So in this diagram, you can see a tame image of CS2 AgBi-Br6 nanocrystals, and this is the image of CS2 AgInCl6 single crystal. And here I have mentioned some more processes for to synthesize the halide double perovskite in both microcrystal, nanocrystal, and single crystal form. You can see, and in this diagram I have specifically mentioned about the synthesis methods to produce this double halide perovskite nanocrystal. So the first one is the ligand assisted reprecipitation method. and the second one is the famous hot injection method, and the third one is the the anion exchange method. So here you can see we have started with CS2Ag BiCl6, and then we are then all the chlorine atoms are exchanged, and we are getting here Br6, and at the end we are getting iodine, that the I6. Okay, so the optical properties of the materials are very important because of these optoelectronic applications. And the band gap is one of the most important property of the materials as it decides about the applications. Also, the absorbance coefficient, PLQI, and carrier lifetime are also important for device fabrication. Okay, so this late halide perovskites had longer carrier lifetime, uh, shallow defect states, strong absorption property, and high PLQI. Because of these properties, these late halide perovskites were very much liked by the scientists for the optoelectronic applications. And in this diagram, you can actually see, like from the DFT calculation, we can now actually predict what is the band gap of late halide perovskite. So here I have shown the band structure of CSPB BR3. You can see here is a direct band gap, which is a value of 2.11 electron volt. And here I have shown how the valence band and conduction band of CSPB BR3 are made. So from this diagram, like this is the partial density of state calculation. So here you can see the 4p orbital of bromine in the valence band and the 6p orbital of lead that makes the conduction band. And our double halide perovskite, they show both direct and indirect band gaps. So yes, here I have mentioned the indirect band gaps that are shown by these double halide perovskites, and these materials, they show direct band gap. Okay. So according to our need, we also have to tune the band gap, or more properly, you can say, to make devices, we often need to tune this band gap. Basically, tuning of the band gap, it implies the controlling of band gap according to our need. Here are some methods to tune this band gap of double halide perovskites. So basically, you can see for the CS2Ag BiBr6, it has a band gap of 3.04 electron volt. And if you do here the thallium doping, you can get here a decrease in the band gap. And if you dope it with 75% indium ions, then you can get here increase in the band gap. And also if you again like dope them with 37.5% antimony cations, then you will get here a reduction in the band gap. So now if you ask why it is important, because since the band gap is decreasing, so it actually increases the carrier lifetime, and it is good for application in the devices, such as you can make solar cells from it. And here is the another example. You can see here the CS2Ag SbCl6, which has a band gap 2.65 electron volt. Then with copper, the band gap decreases to around 1 electron volt. And here you can see the CS2InAgCl6. So this material is actually photosensitive for UV light, and if you dope them with this Mn2 plus cation, then actually they show this photosensitivity to visible light range. This happens because uh, after absorbing the UV light, this CS2InAgCl6 double halide perovskite, they transfers the excitation energy to the d electrons of Mn. And yes, you can also tune the band gap of the nanocrystals. So basically by doping this Cu2 plus, this band gap of CS2Agi and Cl6, that can be reduced to 2 electron volt, from 3 electron volt to 2 electron volt. And also you can change the composition of halide to tune the band gap. So basically here you can see one example, like we have started with CS2Ag BiBr6 nanocrystal, and then we have done the anion exchange. And from here we are getting actually the CS2Ag Bi I6 nanocrystal. And if you see in this picture, you can see uh, uh, like in this solution, there is no iodine, and if you are increasing the amount of iodine, and as a final product, you can see a significant color change. So in this solution, the content of iodine is maximum. Okay. Also, the band gap of nanocrystal can be changed depending on the amount of oleic acid, which is a surface ligand. It actually removes all the surface defects from the surface of the nanocrystal, and as a result, the chance of non-radiative recombination decreases, and the emission property, or the you can say the PL emission, it increases. Also, by decreasing the temperature, the lifetime of the excited state can be increased. So in the low temperature, the amount of trap state decreases, and for that the lifetime increases. So here you can see for the CS2 Ag Bi Br6 double halide, like for this double halide perovskite, you can see when the temperature is high, the life when the temperature is high, the lifetime of the excited state is less, and when the temperature is low, the lifetime of the excited state is high. And there is also one very interesting change, like you can change the material's direct band gap to the indirect band gap. Here you can see we have started with CS2 AgInCl6, then we have done this bismuth and antimony doping, and as a result we are getting here indirect band gap. So if you see in this diagram, so here you can see at first the band gap was high and it was a direct band gap, and when you are increasing the amount of antimony, then it is becoming an indirect band gap, and also the band gap is decreasing here. Okay, so we have got many methods to tune the optical properties. Now we need to check the stability of this halide double perovskite material. So to check the stability, the halide double perovskites were exposed in light and moisture, and their stability was observed. So I have mentioned here some interesting results. So for CS2 AgBi-Br6, so those are stable up to 4 months. They are stable up to 400 degrees centigrade. There is no phase change, and they are suitable for solar cells. And for the CS2 AgInCl6, there is no decomposition till 26 days, and they are stable up to 400 degree. And for the CS2 AgSbCl6, they are stable till 365 days, like that is almost a year, and there is no decomposition up to 250 degree centigrade, and they are stable even if you heat them at 110 degree continuously for 6 days. And also they have shown a great stability in organic and aqueous medium. And yes, here you can also see the nanocrystals, they are also very stable. So basically the stability of the nanocrystal can be tuned by changing the polarity of the solvent and protonic nature of the solvent. And this CS2 AgBi-Br6 nanocrystal, it showed stability up to 3 months in the moisture, high temperature, and 55% relative humidity. And these nanocrystals are stable at 100 degrees centigrade for 300 hours. And if you also illuminate for 500 hours, still they are stable. And there is one also interesting result which I have mentioned here. For the CS2 AgBi-Br6 nanocrystal, you can increase their photoluminescence property by doping them with Mn1YB, but still their stability remains constant. So this doping does not affect the stability. So in this diagram, I have shown the powder XRD of CS2 AgInCl6 material. So here you can see the XRD patterns remain same up to 7 weeks. So you can see here the peak positions, they are not changed. And in this graph, I have shown you the thermal stability of CS2 AgSbCl6. So here you can see the materials are stable up to 250 degree, and after that the degradation started. So this is the TG analysis of CS2SB AgCl6 material. Okay, and here I have mentioned about the most important part, that is the real life applications. So basically, the double halide perovskites, they showed very promising results as photo detectors. So here are some examples that CS2AgINCl6 single crystal, they can work as a UV detector, and the CS2AgINBr6 that can work in visible range. The CS2AgINBr6 thin films, they can also work in visible range, and also this CS2AgBIBr6 and SNO2 heterojunction, they can work as a self-powered UV detector. And here is the diagram of the device where you can see the different layers of materials. And also the double halide perovskite showed a very promising result as X-ray detector. So the CS2Ag BIBR6 single crystal, they can directly convert the X-ray to electric signal. And also this lanthanide double halide perovskite, they showed very high scintillation light yield. So the CS2NaTbCl6, they show green photoluminescence when they are exposed to the X-ray, and the CS2NaEuCl6, they show the red photoluminescence when they are exposed to the X. And yes, their results are very promising because they show high sensitivity, high carrier drift length, low ionization energy, and they can be useful for security scanning and medical sectors. And here is the diagram of how actually a X-ray detector works. And also here are some other examples. So first one is the solar cell. So the CS2AgBIBr6, this double halide perovskite, they show uh, power conversion efficiency of 2.43%. And since their band gap are almost similar to the silicon, so these materials can be suitable to coupling with the silicon. And second one is the LED. So the sodium doped CS2AgINCl6 double halide perovskites. So these can be used to produce the white LED, and they are very stable and can work up to 1000 hours in the year. And also this double halide perovskite nanocrystals, they can be used as photocatalyst. So basically these photocatalyst, they actually reacts with the carbon dioxide and finally break them into carbon monoxide and methane. So yes, the CS2AgBIBr6 nanocrystals, they are actually stable against this moisture, light, high temperature. So from this graph, you can see if you use the crude and the washed nanocrystals, so the washed nanocrystals show better efficiency for methane and carbon monoxide evaluation. And here are the diagrams of solar cells, which were fabricated with CS2AgBIBr6. And this is the main prospect. So we need to explore the stability mechanism, because stability mechanism is the most important issue with the perovskite materials. And also we need to find out more innovative researches that are required on the synthesis mechanism to enhance the performance of halide double perovskites, because we are actually working on the uh, okay, huh. So actually we are working on the previously reported synthesis methods, but you can also modify these synthesis methods. Also, you can identify a new synthesis approach. So these works can be done, and also theoretically many halide double perovskites have been predicted, but they need to be experimentally synthesized. So yes, people are still trying to explore about these materials, and these are the references. And please let me know if you have any questions.
Thank you for the talk.
Yeah.
Debapratim. We are now open to questions. So you can either raise your hand or you can unmute yourself, unmute you to ask your questions, or else you can put it in the chat box. Our speaker will answer them. Thank you.
So yes, the double halide perovskites are better candidate than the regular perovskite because uh, they show better stability than the regular perovskites, and you can also tune their band gap very easily, and that's why they are good for the optoelectronic application. So that's all. Any more questions?
You can unmute yourself and ask the questions directly. We have given you the access. So if there are any more questions, we are open for it. You can wait 1 or 2 more minutes. I think there aren't many. So should we conclude?
Yeah. Thank you.
Okay, sure. So thank you everyone for joining us today for this session. We hope to bring you such informative sessions in future. So stay tuned for that. And thank you, Debapratim Pal, for delivering this talk. It was a really insightful one. Thank you, everyone.
Thank you.